Hey guys, welcome back to another episode of WhyPhi. Today we're going to get into more on the electric Earth. I know I talked about in the last episode, I was going to talk about the mountains, but I figured that I have to start somewhere more basic so that we all are on the same page with a basic understanding of what kinds of forces we're dealing with here. So I figured we start off with just the basics of lightning. So I'm just going to talk about lightning. And just quick disclaimer, this is all purely my interpretation of observations I've made in my lifetime. And it's basically what I think happened, how I think things work from my perspective. Everybody has a different perspective on things, so this is just how my brain is seeing things. You guys might not see it the same way, and that's fine. Anyway, let's get started. So I first just want to talk about the guy who, quote unquote, discovered the lightning figures that we see in the sky. His name was Georg Lichtenberg. In December of 1778, he published a paper on these figures, which he discovered in his laboratory. Basically, he was messing around with some acrylic plates, or I'm not too sure exactly what kind of plates he was using, but he was noticing that the dust was collecting into these discharge-like figures that we're used to seeing, right? And so he devised a way of causing them to happen, and he recorded his findings. He illustrated what he saw and wrote a few papers basically about it. So the discharges that we see in the sky are known as Leichtenberg figures, and one of the famous quotes that he's known for saying is that figures created by positive electricity different from those produced by negative currents, like a sun from a moon. Okay, that's really important. So they're basically like opposites of each other. They're completely opposites, and he's talking about two different forms of electricity, and we're used to just seeing one for these forms of electricity. So basically, Lichtenberg, he was around when Benjamin Franklin was around doing their thing, and they were both studying static electricity or electric discharges. And Lichtenberg didn't actually agree 100% with Benjamin Franklin's ideas, but he was responsible for creating the plus and minus signs that we use when referring to electricity. And he was also said something along the lines of two types of electricity or two modes of one electrical matter that cancel each other out according to the rule of positive and negative values. And then he also stated, I am convinced that this proposition has to take the first place among the few propositions in this field that can be considered a mathematical fact. So basically he's saying that the electricity that we're dealing with has two types. There's the negative and the positive types of electricity. He also said describing electricity is extremely difficult, so... And yeah, it is. It's pretty... nobody really does understand it completely 100%. Alright, so just some points I want to make before I get to the presentation I want to make today. I just want to make some points here on lightning. So just your standard everyday lightning that we're all used to seeing. I mean, these facts, you got to take them with a grain of salt. I'm finding that everybody has their own numbers. All the numbers that when you look up on the internet information about lightning, you're going to come up with 10 different sets of numbers. But basically, just to get an idea on how powerful a single bolt of lightning is, these things can travel. So basically the tip of the lightning bolt can travel. I've got numbers everywhere from 13,000 miles per hour to 270,000 miles per hour. And these are stated from two different sources, so who knows? But and the point is that it's extremely fast. Like it's unrealistically fast. And now the actual lightning bolt itself, or where a lightning bolt is existing, the temperatures within that core can reach somewhere, well, phenomenal temperatures. We're talking like anywhere from 10 to 30,000 degrees Celsius. That's why when it strikes the sand or the soil, it can fuse things together. It collects them and fuses them all together. We're going to get more into that. And the actual bolt itself is only about 2 to 3 centimeters or an inch or so in thickness, and they can range in length from everywhere from 2 miles all the way up to, well, they can actually be shorter than that, but I'm just saying like the average bolt is about 2 to 3 miles long, and they can go all the way up to like 500 miles long, which is just a record that has been set somewhere just shy of 500 miles. One was recorded. Insane. So just to give you a perspective on how hot that actually is, if you were actually able to boil the element of diamond, it would boil at around 3,000 Kelvin. You can't actually boil diamonds, they would shatter. But if you were able to boil diamonds, you would need a temperature of around 3,000 Kelvin in order to do that. And so your average everyday lightning bolt would be more than capable of boiling diamond, which is the hardest substance that we know of. And we're talking like 8 to 10 times over. It'll boil diamond 8 to 10 times up and basically vaporize it instantly. Vaporize diamond, just imagine that. Your typical average everyday lightning, and the kinds of lightning bolts that I'm talking about, the super mega bolts that I'm talking about, are unfathomable how much power is involved. Basically enough to create the entire Earth. Like, it's insane amount of power involved there. All right, so let's get into it. Here we go. All right, so here is basically some of the very earliest illustrations that Lichtenberg made, with some of the very earliest observations that he made when it came to discharges in his laboratory. And this is an illustration he made of what he was observing, and this is kind of cool. So this is really important to keep this one in mind, because I'm going to explain some things later on in maybe another episode about what this is, or show you examples of this occurring in nature. All right, so yeah, just here is another example of his actual photograph of his illustrations. So what we're going to explain here is that there is actually two different types of discharge, two different types of static discharge, one negative, one positive. And there's one figure here that I'm not too sure if it's negative or positive. I don't know what it would be, but it's a really interesting discharge pattern nonetheless, because it has some counterparts in nature. So yeah, so this one here, his earliest example, is kind of like that interesting discharge pattern that I'm not familiar with. I've never seen anything similar to this, but it does make sense, and we'll get into it later, of why this would occur. But here we have two different types of electrical discharges. And this one here is your average everyday positive electric discharge. This is what we would consider, normal everyday lightning for us. And this is actually the only type of electricity that we are familiar with. We have not encountered negative discharges, like on an everyday basis. We don't see negative discharges, so we're not actually very familiar with that. So I'm going to show you examples of that here coming up. But look, so you see this, just keep this image in mind. All these images are just for you to keep in mind for further episodes, but we're just going to get into it. I'm just going to show you different examples. All right, so remember, this is positive electric discharge, where you're used to it. These long tendrils that kind of reach out into, wherever they're going, into the void, into the material that they're getting. This is kind of like what we're used to with heat. The motion of heat through a material and all that kind of stuff takes on this kind of figure. All right, so here's an example of a negative discharge pattern. All right, so they look completely different. If you notice, this is the positive, this is the negative. So right away you can notice distinct differences. We got in your positive discharges, you have these spiny tendrils pointing outward like lines, and then in the negative discharge you have these ring-like structures and circular formations. And then you see it's got like the discharges on the inside, like you're used to seeing. They're just pointed inward. Interesting, hey? These are all Leichtenberg figures from Leichtenberg himself. And then here we got some pictures from photographers of more modern photographers, I should say. Some of these pictures are from 1800s, some of these pictures are from people in modern days, like today, taking photos of these discharges. But anyway, here is another example of positive discharge. This is the classic Leichtenberg figure that you're used to seeing, lightning figure, right? You got your long streamers and you got your secondary streamers coming off of them. Here's an example of negative discharge. They look like feathers, basically. I mean, there's lots of things in nature that we can associate with the negative discharge, which is, we'll get into it in other episodes for sure, but as you can see, this is a negative discharge. Another example of negative discharge. Here's another example of positive discharge. Long streamers, fork-like fingers, split on the ends, always splits in twos. All right, that's one of the rules about this. And the very tip of it will always split into two. It'll never split into like 3 or 6 or anything like that. All right, and here's another example of negative discharge. It's like puffy, feather-like, flowery-like shapes, like a plumed serpent. Make sense? We have the center channel just like in a positive discharge, but looks completely different. So all of these charges have been charged up to the same potential. So the positive potential and the negative potential are equal, and then they take a photograph of each discharge to show you the comparison. So this is the equal amount of voltage. Positive discharge, negative discharge. Look at that center. Really interesting. Tiny little granules, and it seems like they're segregated into rings. And then after a certain boundary is met, these things burst out into long tendrils. And you see it's got like this, I want to say, corona effect, where they have these little bulbs every so often. All right, keep those in mind too. Another example of positive discharge, although this is kind of like a more interesting one. It probably is moving through a different material, but I was debating whether this is positive or negative, but I'm pretty sure this is a positive discharge. And this is a negative discharge. Positive, negative, long feather-like streamers. Again, here is a negative discharge example. Just feathers. They look like, I call them feathers. I mean, they look like pine needles. Lots of things in nature come from this negative discharge. Here's a close-up view of those. Nice little curvy. Everything is just curvy and smooth, you know, or you can even relate this to like old French Victorian style designs, Victorian scrollwork. Those old Victorian scrollwork artists, you know, they might have known something about this, which is really strange. But anyway, next. Here's another example of a negative discharge. I don't know exactly how they were photographed, but they were photographed on plates, and they would discharge onto the plate, and the plate would basically have an imprint or a negative of it, or positive of it, whichever one they used. Here's another example of a negative discharge with these feather-like structures. Of course, all of this is a prime example of fractal geometry. Lightning is the quintessential fractal. It is like the prime fractal. Everything stems from it. This is another example of negative discharge. See how we got like rings, and then from those rings you've got this like inward motion. It's not like a positive discharge where the fingers are reaching outward. These are like drawing inward. Exact opposite. Okay, here's another example of negative discharge. I like to call this the fir tree, because it reminds me of like the center of a tree with tree rings, and then you've got like the branches with the needles coming out the ends. But this is actually a negative discharge. And there's actually examples, maybe I can show it here, but there's examples of a tree that was struck by lightning, and when they cut it open, it had this exact pattern in it where there was like these coronal burn marks around the center. Just another example. Oh yeah, this one actually explains how they made it. So if you want to pause and read, you can read about how they actually made. Yeah, if you want to read about how they made, you can just kind of read it. This is another example of negative discharge. See? So basically, okay, before we get into those examples, basically what I want you to take away from this is that we don't see this in the sky. We don't see this happening around us, this kind of lightning discharge. You know, we're used to the other kinds of discharge, positive lightning. Everything that we see is positive lightning. Okay, so here's a collection of images that we're going to get into just to show you side-by-side comparisons. All right, so we're going to have negative on the left, and we're going to have positive on the right. And these are using the exact same voltages, or in some cases, they were snapped at the same time. So 1927, great example. Outward energy, explosive energy, and this is inward energy, implosive energy. So this is like a heating, this would be like a cooling. They're exact opposites of each other in all aspects, in all physical aspects. All right, here's another example. Positive lightning on this side, negative lightning on this side. Discharges, not lightning, basically static electric discharges, the same thing, same similar effect. Here we go. We got positive discharge over here, and we got negative discharge over here. It's kind of a bad photo, but, and then in between them we have these like streamers reaching towards each other. This would be, I guess, what you would consider the neutralization, or the actual arcs. All right, you see how these arc around here? They're like reaching out towards this side. This is basically the electric field between two quote-unquote charges. Okay, but here we have a positive field, and here's a negative field. And this is their interactions between them. Thin tendrils of streamers, and this is like energy moving between these. This is, of course, on a film that's been photographed, so this would have probably been moving. See how these connected here in a V? Pretty cool. All right, again, same thing. Positive discharge over here, negative discharge over here, and we got, these are from like two coins, I believe, or some kind of coins they used, and you can see these are like feather-like structures, and then this is like a tree, spiny tree-like structure. This is like drawing material inward like a tornado would, you know, and here it's like spreading things out. Leichtenberg referred to these as the sun and moon. You know, here you could see the example, like here, you know, the radiant sun, this one projecting energy, and then this would be like the cooling moon absorbing or drawing in energy towards its center. Keep this one in mind. This is going to be super important for explaining things later on. Here's another example. Positive discharge, negative discharge, sun and moon, hot and cold, explosive, implosive. This is pressure, this is vacuum. It's basically how it works, right? Same example. You'll notice that this is kind of like got a hexagonal-like formation to it. Keep that in mind also. You can see that, right? This hexagonal formation inside. This one's made slightly, has a seventh side here, but it's almost a nice six-sided hexagon. Here also you can kind of see where it's like straightish edges, and it's got these like coronal plumes coming out. Positive, negative. So what happened here is this the thing moved when they did the discharge, so it created this warp. Discharge between negative and positive balls below a varnish plate. So there's an example. You can see on the inside here how this color is similar to this color on the outside. And then on the exact opposite, you've got the white on the inside here and this white plume on the outside. So it's basically showing you that these two discharges are exact opposites of each other. While this one's leading edges are kind of like on the outside, the fingers are all on the outside, pushing outward or drawing in inward, I guess. This one's got it on the exact inside, all right? And it's pushing this energy outward into rings. It's causing like explosive, echoey type structures, rings. And this has got like spiny, long tendrils, all right? All right, here, cool, this is cool. So General Electric did these when they were studying electric discharges, basically. And so this is the exact same voltages. You can see the potentials here, they're basically the same. You can see how they compare with positive and negative. This is a 5 kilovolt, here's a 10 kilovolt, 15 kilovolt, 20 kilovolt, you can read. But basically, you can notice the size differences. So 5 kilovolt compared to the 10 kilovolt, and you can see like the penetration effect, you know, how the 10 kilovolt and the compared to the 15 kilovolt, how it's like got a more dense penetration, right? And 20 kilovolt, like it's almost like if you look at the volumes, it just doesn't make a linear sense. Like it's almost like the potentials grows quite a bit, almost exponentially for the amount of like area it's burned, if you want to put it that way, like how much black area we got going on, right? The outer circumferences are nice and linear. Or another thing to notice, if you look at the density of these branches, you know, see how much more dense these branches are. I mean, this could have been discharging here for a while, but like the discharges could have been overlapping each other. Yeah, and if you notice here on the kilovolt side, on the negative discharges, there's hardly anything. You can barely notice a smudge at all if that's in fact the discharge. But here we got another one. You can notice how these are like curling inward, right? This is all just like curling inward as if it was like sucking in the energy like a vacuum would. Here's another great example. It's all just like drawing it in. Even if this energy is going outward, it might look like it's going outward, but it's in fact like creating a vacuum and drawing it inward and causing these tendrils to look like that. All right, here's just another example of a positive discharge. This is a positive discharge in a straight line. I want you to notice how thick and dense this main branch is compared to the thin outer branches. This is another little interesting feature too, how this almost made a complete circle. You can see how it wanted to make a complete circle. All right, and here's some examples of what they call positive lightning. So to me, this is in fact a positive discharge and not negative discharge. Like I've shown you examples of the negative discharge where it's drawing in the energy into its center, right? Where the positive discharge is like forking outward and spreading outward. Now this has different characteristics, different like discharge characteristics than the cloud to ground, as they call it. You know, when you get the typical lightning from cloud to ground, it kind of like forks out from the cloud downward, right? Well, this is basically the opposite of a cloud, but the forks are going from the ground upward. But this is still positive discharge. This is not an example of negative discharge, even though it's going the opposite way. It's just still a standard old regular discharge that we're used to seeing. I'm going to show you a couple examples here of this positive lightning, they call it. So that goes from the ground up, not from the cloud down that we're used to seeing. So here's just another example. This one, another example. You know, apparently the lightning came from the bottom upward instead of from the cloud down. And usually this happens after a strike from the cloud down. This usually occurs from the ground upward, or if the air is just completely full of, you know, electric energy. Another example of ground to sky, positive discharge lightning as they call it, but this is in fact a positive discharge, an electrical positive discharge. Looks like a tree, eh? All trees grow in this kind of a pattern. They're following that sort of a pattern as they grow in a vortex like. So lightning is actually in fact a vortex. It's like a tornado. It's spinning incredibly fast, and that's why its fingers move through the sky, because it's like crawling its way through the sky because it's spinning its way through the material. Just more examples of positive, quote-unquote, positive lightning reaching up into the sky. The reason why it branches out like this is because it's encountering the resistance of the water. Humidity is going to be my guess. There's a humidity layer here from this cloud, obviously. I mean, clouds are apparently made out of moisture completely, so fresh water happens to be one of the most insulative materials that we know of. Yeah, so naturally it would prevent this from going straight up and connecting with whatever it has to connect with. Another example, You can see where this fork has kind of like joined. I don't know if this is just because of the depth of the photo, but you see they might have joined here and they reach together upward. Just same. Another example of positive lightning, but also positive static electric discharge. This is not negative electric discharge like the feather-like structures I showed you. Another example. Okay, now watch this. So here is an example of positive lightning. This is all positive static discharge. So we got this branching, forking happening, and then when it actually connects with the ground, we have the arc, which is the neutralization arc. Alright, and then here we have lightning again. This is the positive, quote-unquote, positive lightning coming from the ground up. I want to talk a lot about the positive lightning because, you know, people don't really know that it occurs as much as the, you know, cloud down and the lightning that actually strikes the ground and makes an arc that we're used to seeing, right? But this is things that happen when the area gets completely oversaturated. I guess, what's the word? Capacitates. So basically the whole air gets filled with electrical energy. It's capacitating. Is that even a word? I don't know. But it's becoming a capacitor. And this is a breakdown happening. So basically this capacitance is collapsing. The electric field is collapsing and causing this form to happen, right? Here's an example. Basically, this is the same thing as what we just saw, but it's coming from the cloud down now. I'm saying from the cloud down because that's just what people are used to, but believe me, it goes beyond the cloud. It goes much farther than the cloud. This is just a really highly slowed down video. You can actually find this full video on YouTube. It's about a minute long and they slow it down even more, but this is an example of positive electrical discharge, even though this is quote-unquote negative lightning because it's coming from the sky down. And then when it actually connects with the ground, this is a neutralization arc. We're going to talk more about this one little point, but what I wanted to kind of mention here is that this flash that occurs is actually a very interesting event going on right when the initial flash happens. So you got these like fingers leading down towards the ground and you can see them and they're like exciting the air as they go. And then one actually hits the ground, touches the ground, connects with the earth, and we have this like flashback arc. But just before that you have this incredibly high flash. So it's at this point that I think that something really interesting occurs. The lightning bolt hits the ground, and because of its extreme temperature and pressure and everything going on, we'll get into it more about it, it actually vaporizes all the material here, and that material illuminates from being under such an extreme amount of power. And then that vapor is actually sent up this channel because this lightning is actually acting like a tornado. Incredibly fast tornado, probably spinning, well, faster than anything you can imagine. Like, I could say the speed of light. It's probably spinning at the speed of light. And that's, you know how tornadoes work. They create a vacuum and suck everything up. Well, that's exactly what's happening here. This lightning is flashing. It's vaporizing everything, drawing it up, and ejecting it upward. Where it goes after that, I'm not too sure 100%. I do have some ideas. We'll get into them later. But just wanted to mention that early. That lightning is capable of picking up material and transmitting it to another location. And this flash event that you see, this light, is that material being vaporized and transmitted along the channel. Just want to quickly show you the scale of lightning. So I mean, like, we're used to seeing this quote-unquote cloud-to-ground lightning. And this happens within the so-called troposphere here. Alright, and that happens within the range of like 10 kilometers or so. Alright, but we also get these things called blue jets, which occur at the same time of lightning strikes. You know, but not always seen. They're not always seen because not always as powerful as the ones we capture on film. But so we have these lightning bolts, then we have the blue jets, and then above them we have these things called red sprites, and then these so-called elves, which I've never seen actually. I've never seen a photograph of an elf, but we've got lots of footage of red sprites. And so what you're seeing here is a continuation of energy that comes from extremely high in the sky down to the cloud. And the cloud is like 1/4 of the story. It is only the intermediary between this energy and the ground. You know, this is extremely like high voltage, extremely high voltage energy getting transformed down to a lower voltage and extremely high amperage. All right, so it's like when this event occurs, it goes all the way down to here, or vice versa from the ground up. We see it visually from the ground up, but the energy actually comes from sky down. And all this electrical event is occurring at the same time. And these clouds are basically just like condensation effect of this. You know, this cloud vapor you're seeing is like smoke or some kind of barrier being formed between two mediums that meet each other. And we see them as clouds. And I'm just showing you the system involved here. So it's not just cloud to ground lightning. It's all this other stuff involved too. So we got energy being transformed down and creating massive lightning storms where all these tiny little bolts are going off between this massive electric field that's being generated here. Okay, that's one thing I really want you to get. So here we're just showing you examples of red sprites. And in these, I believe we see both positive and negative discharges occurring when there's some kind of medium barrier here between the two. And I'm not sure if this is actually simulated by NASA's simulation or if this is a real photograph, but I got some real photographs in here because these just look really well defined. But anyhow, here's another examples of some red sprites that are occurring above, thunderstorms below. All right, so we got this positive discharge fingers here, and we got like negative discharge on the top. Pretty certain that's what I'm observing it to be. You know, here, same effect. We have the positive discharge coming from below. You can barely see these streamers. And then here also we have the negative discharge from on top. It's like roots of a plant. You know, we got the roots of a plant, the ground, and then you've got the plant growing on top. Here's another example. Positive discharge, negative discharge, thunderstorm below, or a lightning storm, same thing. Here we've got, again, positive discharge, negative discharge on top. So that's what the red sprites remind me of, both discharges combined. Great example. What's cool about this is that there's like ancient stories of people saying blood raining down on the earth. You know, this gives a great example of what that could have looked like to them from extremely high electrical activity in the sky. We'll get more into that in other episodes. But yeah, check these out. Positive discharges on the bottom, negative discharges going up. Pretty neat. Here again, I'm not too sure what this aurora is capturing, you know, but this is one massive negative discharge and one massive positive discharge. And there's some kind of medium here. I don't know if it's gassy layers or something, but there's two layers here they're meeting at and they're discharging between. All right, here's another great example of red sprites above thunderstorm. Another great example of them, red sprites, thunderstorm way off on the horizon. So you kind of like, you know, you're seeing this high altitude because the thunderstorms are way off on the horizon, probably 100 kilometers away by this point. Maybe not that far. Probably like 30 or 40 kilometers away. Yeah, and then these would be, you could see them up at an angle. But anyhow. All right, cool. So here we're going to check out some blue jets. All right, so this is from the cloud right here. After a lightning bolt has discharged to the ground and it arced from the ground, this blue jet will appear. And this is what I'm talking about, where it's ejecting material. So all that vaporized material then gets transferred up this blue jet and ejected high into the sky, like it's drawing it upward. Still being illuminated, of course, and then it spreads out into a vapor. So it's just like putting it into the sky. We got some green aurora discharge here. I'm not too sure if that's part of this or not. Another example of a blue jet, gigantic blue jet. So here we got the bolt occurring in the cloud. And then we got the blue jet streaming outward. You got this nice feathery projection here. I don't know if this is an example of negative discharge or not. I'm thinking it might be. So it's like a negative discharge pattern. And the positive discharge pattern going down. We got the cloud as the intermediary. You see that? Yeah, so these blue jets might in fact be a negative discharge, all right? And then everything below the cloud would be the positive discharge that we're used to seeing, and this cloud barrier being the intermediary. Another example of a gigantic blue jet that's actually reaching up and contacting the red sprites. That's what we got. This blue jet goes up and it touches the tips of the red sprites, and in some cases you can't always see it, but that's what goes on. So we got the red sprites that appear up here, blue jet ejecting upward. Yeah, this is actually a really cool example of a blue jet. This blue jet and a thunderstorm occurred. So blue jet ejecting upward and coming in contact with the red sprites above it. Again, another example of that. So this actually looks like a, you know, plasma ball. If anybody has ever seen plasma ball, you got those blue filaments inside with the red tips. Typical plasma filament. Here again, just to give you, you know, get this image burned into your mind of how these thunderstorms are not just lightning, cloud to ground lightning. The story is way more complicated than that. Okay, cool. Now we're just going to quickly take a look at some examples of Leichtenberg figures that people are making as hobby projects or art projects. And they basically have some high voltage DC or high voltage AC. Depends on what kind of system they use. And they can create burn patterns like so in wood. I just want to show you. So this is like, you know, one terminal, and these are leading towards each other. There's some pretty cool things to note about this. All right, so just like I want you to see the patterns that are being burned. So as you see, the tips of these lightning is I guess you can consider it lightning. It's kind of working the same way. It's a discharge happening. This is probably an AC where it's flipping back and forth, but whatever. Regardless, the tips of these are burning into the wood. It's making its way through the wood, and it's converting that material into carbon and then drawing out all the gases that it creates back down this tendril. Right? And this is spinning inside like a tornado. But anyway, it's sucking this gases down, and you see they're probably being burned off here. This smoke is all the gases being burned off. And it's creating these nice tree-like structures. And this is a positive discharge. Positive discharge electricity. Here's another example of it making its way through the wood, basically converting all that into the gases, and it's leaving behind the carbon that it can't, and it's using the carbon as a medium to transfer down, like it's using it as its conductive substance. And then all the gases that it boils, vaporizes, they just become gas. They burn off. Here's a great example of lightning striking the cement. I want you to notice how it's turned this cement into like glass pretty much. It's this black, thick glass, like volcanic substance looking almost. Nice pattern it left behind. It basically like burned its way through this cement, melted it all. The temperatures required to melt this stuff is incredible. Like, to melt it into this glassy, bubbly substance requires such a tremendous amount of heat without it actually cracking this thing. Here's a great example of two terminals that were making their way towards each other. It's kind of interesting that they never actually did combine. Maybe they probably shut the power off before that happened, but you'd think that they would immediately do this with the amount of power that's going on there, but no, they're worming its way through this substance. It's actually interesting that it does not want to connect, actually. It wants to keep itself away for as long as possible, which is weird. You'd think that it would work the opposite, but it doesn't. At least from my observations, it doesn't. So check this out. So we got this nice channels being carved. This is a beautiful example of a fractal. Fractals are basically, they come from the idea of lightning. Lightning creates all the fractals you see in nature. It's a complete 100% electrical effect. Another great example of it. So, so here's this long channel, and then we've got these blowouts. This is basically an exact representation of rivers and how rivers were formed. And we'll get more into that, but keep that in mind, that this is how rivers were formed with lightning tendrils. So they would go through and they would burn their way through the earth, converting everything into rock, stone, and then drawing out all the major essential elements that it could, transferring them back down this channel, all in the form of gases, metals, all that kind of stuff. They were sucked out of the soils and converted into amalgamates, all by lightning. We're going to get more into it in the future videos. But so what they would do is just wash this board down with moisture, and they would turn on the electricity. They got a terminal over here and a terminal over here, and then they would just snake its way through. But it doesn't make a direct beeline for it. It actually takes its time. I'm just showing you how this channel is carved. Just keep that in mind, and how this point is burning its way through. It's forcing its way in, and actually it's kind of like converting the tip to. It's super exciting, the tip here, to a point of such a high temperature. It's spinning it up to such a high temperature that it instantly vaporizes, and then because of that, it creates a carbon deposit and then gives the bolt an opportunity to move forward, right? Because it's created a pocket in front of itself from spinning up that material to such a high spin, that allows it to continue moving. We're gonna get way more into this in future videos. I know this video is becoming quite long and I'm blabbing on here, but I just want you guys to really get the idea of what lightning is capable of doing. And I'm sure there's tons and tons of things I'm forgetting, but I'm going to save that for other episodes. Leave a like, share, subscribe, and all that jazz. Put your comments down in the comment section below. I'm interested in hearing what you have to say. Of course, I'm going to be talking about lightning throughout this whole series, so the stuff that I missed today, I'll talk about in other videos, so no need to worry. All right, folks, thanks for listening and all that jazz, and we'll see you in the next one. Bye-bye.